Welcome to the Problemers Channel Season 2, Episode 48, the episode which I titled A Circle Dance of Flying Squirrels, because in this episode we will solve an absolutely beautiful mathematical problem that deals with a bunch of flying squirrels hopping around some number of trees that are located over the periphery of a circle. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material presented on this channel is to go to the homepage of this channel and in the channel's trailer section, finding the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E48, we're told that in the initial state, in the one flying squirrel per tree fashion, 666 flying squirrels sit on 666 trees that are located over the periphery of a circle. Then every second, let's say, or every minute or every hour, doesn't really matter. Pick your favorite unit of time, but for definitiveness, let us agree that every second the following one jumping sequence unfolds. So what is a jumping sequence? One jumping sequence is the act of one random squirrel jumping from the tree that the squirrel is sitting currently on to the nearest neighbor, counterclockwise, let's say in this direction, from this tree to this tree with no trees in between, and at the same time another any which one random squirrel jumping from the tree that it's sitting on to the nearest neighbor in the opposite or clockwise direction. So here it is important to understand that when the squirrels jump, they jump in the mutually opposite directions. One squirrel jumps, let's say, counterclockwise in positive direction, and another squirrel is jumping in the clockwise direction, in the negative direction, and both jumps are executed in such a way that both squirrels land on the immediately adjacent tree with respect to the direction of the jump. Again, one more time, let's say that a squirrel that decided to jump sits over here on this tree, then this squirrel will fly counterclockwise in the positive direction. Let's say in complex analysis, we usually take it to be a positive direction from this tree to the immediately adjacent, immediately neighboring tree over here. And at the same time, some other squirrel, let's say the squirrel is sitting over here on this tree, will jump and fly in the opposite or clockwise negative direction from this tree to this tree with no trees in between, and this tree will be the immediate neighbor of this tree in the clockwise direction. Question: under the jumping rules specified, is it possible for all the squirrels to gather on one and the same tree in a finite amount of time? Which is the same thing as asking whether it's possible for all the squares to gather on one and the same tree in a finite number of jumps or in a finite number of jumping sequences. Now, this problem is also open-ended, and we know that a problem is open-ended if the exact scenario that will unfold in the problem is not specified, and the burden of detecting which way this scenario will unfold in the positive direction or in the negative directions is on us, the problem solvers. That means that if we think that it is possible for all 666 squirrels together on one and the same tree in a finite amount of time, then we need to present at least one algorithm, if you will, or at least one jumping sequence, which demonstrates correctly and convincingly that yes, here is a way to take all 666 squirrels, and by using the rules specified in the problem statement, put them on one and the same tree in a finite amount of time. Conversely, if we think that it is impossible for all 666 squirrels to gather on one and the same tree in a finite amount of time, then the burden of generating a correct and convincing proof that no matter how these flying squirrels hop around the given trees, they cannot possibly um, gather on one and the same tree. That burden is on us. As I mentioned a few seconds ago, this problem is open-ended, and it is a good idea to structure your academic curriculum in such a way that you try to solve as many open-ended problems as possible. Of course, if the curriculum permits that and the problem itself is not too difficult, so that you do not have to spend too much time on deciding which way the problem will unfold, so that you can keep up with the rest of the workload in your curriculum. But in the grown-up mathematics, theoretical physics, and computer science, this is precisely the scenario that you will be dealing with, an open-ended situation, and it is a good idea to put your mind into the state where you're used to dealing with open-ended problems. But in addition to being open-ended, this problem may seem very strange to some of our viewers who are not used to solving mathematical problems yet. And these viewers may say, Roman, look, you did not really tell us any specifics about how the flying squirrels hop around the given trees. We do not know which squirrel will jump one way in one direction counterclockwise and which other squirrel will jump in the opposite or clockwise directions. How on earth can we tell you if it is possible for all the squirrels to gather on one and the same tree or not? This is a valid observation, yes, but at the same time, I will reflect it back to you guys and ask you the counter question. What do you think? Why this problem was stated in this specific way? Possibly there is a hint that even though it may seem at first blush that some information in the problem statement is missing, the author of this problem evidently is convinced that it is possible to solve this problem with absolute certainty with the perceived lack of information that you are looking for. And this is precisely the indication that it is a good idea to try the invariant problem solving approach with this problem, or half invariant. Now in season 2, let me write it down over here for you guys. Season 2, episode 44. Season 2, episode 44. I explained in detail how does the invariant problem solving approach work. If you missed that episode, it may be a good idea for you to go and watch that episode and work your way through the consequent problems. I always start the new material with very straightforward problems so that you do not have to fight many battles. You just have to fight one battle, the new problem solving approach, and the local subject matter is nothing beyond kindergarten or lower school variety material. But here in the lightning round, when we want to try to apply the invariant problem solving approach to the process of generating a solution to this or that technical problem, we should try to partition or sort all the material in the given problem into two distinct piles. In one such pile, we put all the local material that does vary, and into another such pile, we put all the local material that does not vary. Any magnitude that within the given context does not vary, we refer to as an invariant. And by now we know that not all invariants are created equal, in the sense that a useful invariant is an invariant that can produce two distinct values. One such value should be produced by the initial state of the problem, and the second distinct such value should be produced by the target or by the requested configuration. If a invariant can discriminate between two states, the initial state and the requested state, then it may be useful. But if an invariant cannot distinguish or detect the difference between the initial and the requested states, then that invariant will not be useful, and we will see exactly how does this usefulness come into play in this specific episode with this specific problem. As such, let us take a look at what material in this problem does vary. After we think about what is going on in this problem, we should realize fairly quickly that in its most general case, when we have at least four distinct trees, and if there are no common or shared trees involved in one jumping sequence, after one jumping sequence, the distribution of squirrels over these four trees that were involved in this one jumping sequence will change. This is definitely the local material that will change. How can we see that? Well, I'm about to say something and then I'll ask you guys to explain what just transpired. Let's say there were X squirrels sitting on the tree, let's say 7, and there were Y squirrels sitting at the tree number 8. What just happened over here? The correct answer is the following. What happened over here in that sentence is an implicit assumption that I'm about to make explicit. In this problem, we will treat the trees as distinct objects, but we will treat squirrels as indistinguishable. Because we will treat our trees as distinct, we will be able to assign our favorite consecutive initial whole positive numbers to them and number our trees 1, 2, 3, 4, 5, 6, 7, and so on with the elements of the set of whole positive numbers. But the squirrels will be indistinguishable, and we only care about their number on, let's say, target tree if somehow magically they all can gather on one and the same tree. Now, let's mark it down so it's more visually explicit. This was the tree number 7, and that was the tree number 8, and the jump took place which way? Clockwise, from the tree number 7 to the tree number 8. Again, what just happened over here? Something did happen, and most people will not even think twice. But remember, when you are trying to solve the problem, always the initial battle is loose. It's not very rigorous. It's fast. We try, we fail, we try and fail. But then when we're ready to write up our solution, let's say submitted for publication, if you will, then we have to make things watertight, explicit, rigorous, and all that jazz. But what happened over here is that another implicit situation was, we slided another implicit situation into the woodwork. We agreed that we number our distinct trees in the clockwise fashion 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But even now, it should be evident and understood that the way we number our trees, clockwise or counterclockwise, should not really matter. For definitiveness, I will number my trees in this experiment in the clockwise fashion. You guys can try numbering your trees in the counterclockwise fashion just as well. So let's say one squirrel jumped from the tree number 7 to the tree number 8. Then what happens? Well, the tree number 7 was tree number 7, and it is still a tree number 7. That tree, the number of the tree did not change. And the tree number 8, it was number 8 before a jump, and it is still number 8 after a jump. But what happens to the number of squirrels? The number of squirrels from which this flying squirrel took off is decreased by 1. So now that number reads x minus 1 at the tree number 7. And what about the number of squirrels on the tree number 8? Well, that number was increased by 1, and now it reads y plus 1. So distribution of squirrels over these two specific trees did change. Evidently, of course, we will see that if a random squirrel, let's say, jumps from the tree number 8 in the balancing act to the tree number 7, then nothing happened. This is a transposition, and we'll talk about it in a few seconds. But let's say right now, as a balancing act from the tree number, I'm inventing things on the fly here, tree number 19, the balancing act was executed in such a way that a squirrel jumped from the tree number 19 counterclockwise onto the tree number 18. Then what will happen here? At the tree number 19, we had Z squirrels, and at the tree number 18, we also had some number of squirrels. So after the jump, what happens? What happens after the jump? Here we'll show the transition for the jump. So the number of squirrels on the tree that from which this flying squirrel departed decreased by 1. So now, even though the tree is still number 19, what happens here is that we have Z minus 1, squirrel Z minus 1, and what happens over here? Well, it was a tree number 18 before the jump, and it remains the tree number 18 after the jump, but the number of squirrels on the tree now would increased by 1, you see. So what is the most general case? The most general case, when there are no shared or common trees involved in the jumping sequence, what do we have? We have 1, 2, 3, 4 distinct trees. The distribution of squirrels over which did change after one jumping sequence. So now we see that, okay, this material, this local material, does change from one jump to another, or every second, let's say every second this material does change. But now we want to see what material does not change. And it's not that evident, and maybe not as straightforward to find what quantity does not change. So we do the next best thing, and actually a popular thing that mathematicians do when they take on a new problem, and that is we will play with small numbers first. Before we discuss our first case, I would like to observe that to many newcomers to solving problems in particular and to mathematics in general, it may seem that solutions to technical problems in mathematics, theoretical physics, and computer science pop out of nowhere, out of the blue in an instant. Unfortunately, this is not the case in mathematics, theoretical physics, and computer science. Nothing is easy, nothing is quick, nothing is fast. That is why on this channel, barring these few seconds, you will never hear the words from me, easy, fast, and quick. Everything in mathematics, theoretical physics, and computer science is hard, difficult, and takes time. And if you do not have the taste or the stamina to deal with hard, difficult, and long time, then you either should develop that stamina and that taste and that desire to work with difficult, hard material for a long time, or you should probably look for something else to do, because the hard sciences are not for you. As such, again, it is not the case that we read the problem statement and then instantly, boom, oh yeah, look, there it is. There is a useful invariant. Never happens. The only way to come up to, the only way to even have a chance of inventing, discovering, pick your favorite verb that describes the situation, or constructing a useful invariant, is through development of an intimate knowledge with the problem. In theoretical physics and computer science, there are their own means, or there are their own ways of developing the intimate knowledge with the problem. And in mathematics, one such way to develop an intimate knowledge with the problem is to start experimenting with small numbers or small sized objects. So here, let's say one squirrel and one tree. So let's say it may sound a little funny, but yes, let us do just that. We have one tree, one good old tree. It's indexed with 1 because this is one tree. We have one squirrel sitting on that tree. And evidently, what do we see right away? We see right away that this problem begins its life and ends its life in the solved state already, because it is the case right away that all the squirrels have gathered on one and the same tree. In other words, in this case, when the number of squirrels, let's say n, is equal to 1, then the problem is solved right away, and the answer to the general or similar question stated in this problem is in the positive. Yes, it is possible to gather all the squirrels on one tree, and in this case, one squirrel on one tree is gathered on one and the same tree pretty much instantly in the amount of time equal to big fat 0. This problem is in the solved state. Yes, all the squirrels have gathered on one and the same tree in a finite amount of time. Now that we analyzed the case of n equals 1 squirrel and 1 tree, we will move on to the case of n equal 2 squirrels and 2 trees. Now, when we're given 2 trees and 2 squirrels, then in the 1 squirrel per tree in the initial state, we have 2 squirrels sitting on 2 trees. I'll draw the second tree over here. Somehow it's right here. We treat the trees as distinct mathematical objects. As such, we name one tree as 1, the other tree as 2. We have 1 squirrel sitting on the tree number 1 and 1 squirrel sitting on the tree number 2. What are the choices in this case? Well, amazingly enough, in this case, it is possible to carry out a complete computational analysis of how these things can unfold, how the events jumping sequences can unfold in this problem. Let's say the squirrel number 1 decided to jump in the clockwise direction this way. Clockwise this way. What is the immediate neighbor, the immediately adjacent tree for the tree number 1? The immediately adjacent tree for the tree number 1 is the tree number 2. That is the only choice. There are no other choices. And that means that according to the statement of the problem stipulated earlier, there is only one choice for that squirrel, is for the squirrel sitting on the tree number 2 is to jump counterclockwise in this direction and land where? On the tree number 1. So the squirrel that was sitting on the tree number 1 flies onto the tree number 2, and the squirrel that was sitting on the tree number 2 flies onto the tree numbered as 1. Does anything change in this case? Well, in this case, the distribution of squirrels over trees does not change. This is precisely in the theory of permutations and in the theory of groups. What will this be called? This will be called this will be called a transposition. And the other case, let me show it maybe with, let's say, blue. We can also analyze the other case where the squirrel that sits right now on the tree number 1 decides to jump counterclockwise this way. Then again, according to the problem statement, according to the rules stipulated in this problem, the only other choice here we have is for the squirrel number 2 to jump clockwise in the opposite direction. And again, because of the geometry of the object in this case, the immediate neighbor of the tree number 1, not the tree itself, but the distinct object over here known as the tree number 2, and the immediate neighbor for the tree number 2 with respect to the clockwise direction is what? Is the tree number 1. So what will happen over here? Our indistinguishable, remember, our indistinguishable squirrels will swap or transpose their positions with respect to each other. They will trade places, but overall, the distribution of squirrels over, or the overall distribution of indistinguishable squirrels over distinct trees will not change, evidently. So in this case, what is the problem? We also solved this similar problem, of course, not the 666 trees, but with the smaller numbers for our experimentation purposes. We solve the problem when n is equal to 2. And in this case, what is the answer? Well, unlike the answer that we gave in the previous case, the answer in this case is in the negative. No, it is evident that in no finite amount of time, it is possible for all the squirrels together on one and the same tree. Over here, this is simply impossible. No matter how these two squirrels jump around according to the rules specified in the problem statement, they will never be able to gather themselves or wind up hopping onto one and the same or onto a single tree. So in the case of n equals 1 squirrel, it is possible, and the amount of time that is needed is 0 for that configuration to take place. In the case when n is equal to 2, the answer to the similar question is in the negative. It is impossible for two squirrels together on one tree using the rules, the legal rules specified in the problem statement, in any finite amount of time. Now that we understand what is going on with two squirrels and two trees, now let us analyze the situation that will unfold if the number of trees is increased by 1 to 3 trees and 3 squirrels. With n equal to 3, n equal to 3 squirrels and 3 trees, it becomes evident almost right away that the answer to the similar question posed in the problem becomes positive. Yes, it is possible to put all 3 squirrels onto one and the same tree in a finite amount of time. And the way we do it is as follows. I'll use the red chalk to draw a little anchor. So here we anchor one squirrel. Let's draw the squirrel in red over here on the distinct tree number 1, because the trees are distinct. Remember, they're numbered 1, 2, and 3. Let's say we anchor a flying squirrel onto the tree number 1. This squirrel will not jump anywhere, and in the initial state, in the one flying squirrel per tree configuration, we have one squirrel sitting on each tree. So the squirrel is over here and the squirrel over here. And what do? Well, while the anchored squirrel sits on the tree numbered as 1, our squirrels that sit on the trees numbered 2 and 3 execute one jumping sequence. It takes exactly 1 unit of time to do so. And let's say the squirrel that sits on the tree number 2 jumps counterclockwise, and the squirrel that sits on the tree number 3 jumps clockwise, like so. And voila, what do we have after that sequence of jumps? We have 0 squirrels on the tree number 2, we have 0 squirrels on the tree number 3, and we have precisely 3 squirrels. Let's draw them 2 and 3. We have precisely 3 squirrels that sit on the tree numbered as 1, and this is precisely what is required of us to do in a similar fashion. And that is, we see that in the time t equal to 1 unit of time, let's say in 1 second, it is possible to put all 3 squirrels onto one and the same tree when the number of squirrels is 3. Now that we understand what is going on with 3 trees and 3 squirrels, we'll take on the next case of n equal to 4 trees and 4 squirrels. When the number of squirrels and trees is equal to 4, on the wings of the previous success, we try to execute exactly the same maneuver, let's say n equal to 4, and we take our 4 distinct trees, we number them as, let's say, 1, 2, 3, 4 distinct trees. they sit on the periphery of a circle, and in the initial one flying squirrel per tree state, we have one squirrel sitting on each tree. Again, we anchor one arbitrary, doesn't really matter which one, we anchor one squirrel in place. Let's say we anchor this character right here, the squirrel sitting on the tree number one. And then what do? Well, in a pathetic attempt to put all four squirrels on one tree, we'd say what? The squirrel that sits on the tree number two jumps counterclockwise onto the tree number one. The squirrel that sits on the tree number four jumps clockwise onto the tree number one, because with respect to the counterclockwise direction for the tree number two, the tree number one is the immediate neighbor, and with respect to the clockwise direction for the tree number four, the tree number one is the immediate neighbor. But then at this time, how many squirrels do we have? One more squirrel here, one more squirrel here. The squirrel on the tree number four is gone. The squirrel on the tree number two is gone over here. But what do we see? Well, we see the poor cousin Billy over here. The squirrel on the tree number three did not really wind up on the tree number one. And how can we move that squirrel onto the tree number one legally while keeping all the other 1, 2, 3 squirrels on that tree number one? That does not seem to be possible at all. At least right now, we do not see such a way. If, for example, initially, forget about anchoring anything, if we take our squirrels and then they trade places or transpose themselves, we already know that this is a no-op, that there is no meaning to do so. The trees are distinct, the squirrels are not. When the squirrels transpose their positions, trade their spots, nothing, no change is introduced into the problem. We're not moving closer to solving the problem in a positive way, in the way of putting all the squirrels onto one and the same tree. This is not good. This is one potentially, we think, hopeful way. But if at this point, for example, the squirrel number three jumps onto the tree numbered S2, so the one squirrel over here has to jump this way, we will have two squirrels on the tree number one, two squirrels on the tree number two. In some sense, we are, in a way, vaguely speaking, are back to the previous case of two trees and two squirrels, where they transpose their positions, but they can never gather on one and the same tree. So here we have this uneasy and not so happy feeling that on the one hand, it looks like it is impossible to put all four squirrels onto one and the same tree in this case. On the other hand, we do not really have a solid proof, but we decide to put this situation on the back burner to see what happens next, and we take on the case of 5 trees and 5 squirrels. Wonderful when the number of squirrels is 5. Then we right away see what is going on. We have 5 distinct objects, 5 trees. And by the way, notice how another thing happens almost all by itself. Psychologically, it's very convenient and very inviting to space the given trees over the periphery of the given circle evenly, but we're not told whether the trees are spaced evenly or not. So again, on the one hand, that may be a point of discomfort. We're not told how the trees are distributed over the periphery of a circle. On the other hand, as we already see, this doesn't really matter, and we use it just as a vehicle for demonstration purposes. But if we have 5 distinct trees, let's say we number them 1, 2, 3, 4, and 5 in the clockwise fashion. Again, we pick one arbitrary tree. It doesn't really matter. Let's say it's going to be the tree number 1. We anchor the squirrel that sits over here. I'll show the squirrel in red on the tree number 1. That squirrel is not going to fly anywhere. we have a squirrel on the tree number 2, one squirrel on the tree number 3, one squirrel on the tree number 4, and one squirrel on the tree number 5. One flying squirrel per tree in the initial configuration. Ready, set, go. Boom, we see what is going on. In the time t equal to 1, what's going to happen? Well, the flying squirrel that sits on the tree number 2 will fly counterclockwise. And with respect to that tree, what is the nearest neighbor? The tree number 1. In the balancing act, we'll send the squirrel that sits on the tree number 5 flying clockwise onto the tree number 1. Why? Because with respect to the clockwise direction, for the tree number 5, the tree number 1 is the immediate neighbor, and after the time t equal to 1 in 1 second, we have 0 squirrels on the tree number 5, 0 squirrels on the tree number 2, but what do we have? We have 1 squirrel sitting on each tree number 3 and number 4, and what's going to happen now? Well, we see that already in one jumping sequence, our squirrels will get to the trees number 2 and number 5 respectively, and in another jumping sequence, bam, both squirrels will wind up on the tree number 1. So in the time t equal to, first, again, we see these squirrels will get to the trees number 5 and 2 respectively. This is one unit of time over here. And at this point, in some sense, we are back to the 3 problem. Remember, a few seconds ago, in the previous segment, we considered the 3 squirrels sitting on 3 trees in the initial configuration, and that's what we have. Here is the squirrel that used to sit on the tree number 4. On the tree number 2, there is a squirrel that used to sit on the tree number 3. So here, no squirrel, one squirrel, one squirrel. And in the second one, this is what? 1 plus 1. This is precisely 1. And this is another unit of time. In the second unit of time, bam, we have all 5 squirrels happily sitting on the tree number 1, and no squirrels on the tree number 2, 5, 3, and 4. Problem solved, and the answer is given in the positive. What is the sum total? 1 plus 2 is 3, and a tau equal to 3, and this is definitely a finite, perfectly finite number. In 3 units of time, we managed to put all 5 squirrels onto one and the same tree using nothing but the legal jumping sequence described in the statement of this problem. And we now understand that the numbers that we looked at previously, the odd numbers 1, 3, and 5, are nothing special. We can grab any other good old finite odd number, 7, 9, 11, 13, 15, and so on, and put all the squirrels on that odd number of trees onto one and the same onto a single tree in a finite amount of time as follows. If the number of squirrels and trees is odd, then it means that that number is representable as 2 times m plus 1 for a suitable integer m, shown as red over here. And that means precisely that due to the shape of that number, we can take the proverbial plus 1 and anchor one arbitrary squirrel to an arbitrary tree. Let's say we'll call that tree number 1, it doesn't really matter. But the moment we do that, the moment we anchor one squirrel to one tree in an arbitrary fashion, that means that we logically partition the remaining squirrels and trees in their initial configuration into 2 piles of equal size. There will be precisely m squirrels and trees to the logical right of the anchor tree and the anchor squirrel. And there will be precisely m squirrels to the logical left of the anchor tree and the anchor squirrels. In other words, we can partition the remaining squirrels into logically right squirrels and left squirrels as shown over here. And then we can also, even though we're not told how exactly the trees are spaced over the periphery of a circle, but it doesn't really matter because we can take each and every, let's say, left squirrel and pair it up with precisely one right squirrel based on what? Exactly, based on the proximity, to the anchor tree and the anchor squirrel. In other words, the trees physically can be distributed in any which funny way. It doesn't really matter. They do not have to be spaced equally over the periphery of a circle. But in terms of the immediate neighbor clause or requirement, we can always take, for example, this blue left squirrel and find the squirrel from the right pile that is the nearest neighbor to the anchor tree and the anchor squirrel. And these two squirrels, the blue right and the blue left squirrel, will form a pair as shown over here in blue with the dotted line. And like so, we can partition all the remaining squirrels. We'll take the next closest or the next further away squirrel from the left pile, find its buddy from the right squirrel's pile, and these two squirrels will form a pair, and so on for all the remaining pairs. These squirrels can be logically connected as shown: yellow, carrot, or orange if you will, and green. And then what happens? Well, there are many ways, there are many algorithms over here. The algorithm that I have in mind is not a unique algorithm. There are other ways to do it, but the way I see it is as follows. At the time click number 1, we put the nearest two blue squirrels onto the anchor tree, time unit number 1, as shown by the blue arrow. Wonderful. What do we do next? Well, now that they vacated the premises, so to speak, we take the two yellow squirrels, one yellow right squirrel, one yellow left squirrel, and in how many units of time do we put these two squirrels onto the anchor tree? In 2 units of time, exactly, as shown by two yellow arrows on each side. Time number 1, they get onto the trees where the blue squirrels used to sit, and time unit number 2, they jump onto the anchor tree. And what do we do next? We grab the carrot colored squirrels and we repeat the same experiment with them. The trees where the yellow and the blue squirrels used to sit are empty. There are no squirrels there, and then these two squirrels just simply hop once onto the trees where the yellow squirrels used to sit, another one jump onto the trees where the blue squirrels used to sit, and onto the third and final jump, they will be sitting where? Precisely, they will be sitting on the anchor tree. We repeat the same experiment for example, these two green, one green left squirrel, one green right, logically, of course, right and left logical terms, logical right green squirrel. And in how many units of time do these two squirrels in a legal fashion get to the anchor tree? Well, 1, 2, 3, and 4 by the number of yellow arrows shown over here on each side. And that way we are assured that at every unit of time, or after each and every jumping sequence, we leave more and more trees with no squirrels behind them, and we get to one and the same tree, and boom, in a finite amount of time. That way, when the number of squirrels and trees is odd, we manage, that's one algorithm, to put all these squirrels onto one and the same tree in a finite amount of time. And what that time is? Well, that time evidently is given by a very straightforward sum, k, where k varies from 1 to m. 1 to m is over here, and we already know what that sum is. There should be no mystery behind this expression. 1 plus 2 plus 3 plus 4, and how many of these pluses there will be? M, exactly by the number of squirrels on each side with respect to our center or logically centered squirrel, so to speak. We already know the number. We can write this formula down. We deduced that sum in season 1, or I think, or early in season 2, borrowing the notion of center of mass from physics. We know that much, and that is the solution of this problem. In other words, what we can state is the following: if the number of squirrels and trees is odd, That means that it is representable as 2 times m plus 1 for a suitable integer m, and this is an algorithm according to which all 2m plus 1 squirrels can be put onto one in the same tree in a finite amount of time, and this number is definitely less than positive infinity. This is a nice, beautiful, finite number. Problem solved. And the answer to that part of the problem is in the positive. But we're given 666 squirrels in trees. The number is even. So now we have to come back to even numbers and see what is going on with an even number of trees and squirrels. And in that respect, we circle back to our original point of adventure. What does not change in this problem as our squirrels execute their legal jumps? Well, in this problem, you do not have to be an Einstein to realize right away that two things remain invariant in this problem, no matter what, at all times under any jumping sequence. The number of trees and the number of squirrels. The number of trees is again evident. We have 666 trees at the beginning of the jumping sequence in the initial state, and we will have 666 trees if somehow magically all 666 squirrels can bunch up on one and the same tree. The same idea, the same observation holds for squirrels, and again for the nitpickers of the world, they will be happy to hear that these are good old mathematical squirrels, and we look at that neighborhood or happy family of squirrels during the time frames that are short enough so that no squirrels die and no squirrels get born as they jump around. These are good mathematical squirrels, and we have 666 squirrels at the beginning of the experiment, and we will have 666 squirrels precisely at the end of the experiment if somehow miraculously they can all bunch up on one and the same tree. So these two quantities, the number of trees and the number of squirrels, are what? Each such quantity is an invariant. Technical, yes. Neither quantity changes. It's an invariant. But let us go back to our early observation that not all invariants are created equal. What does it mean? Well, when we say that not all invariants are created equal, that precisely means that some invariants are capable of discriminating or detecting the difference between the initial state and the requested states, and some such variants cannot see or sense or feel or produce the difference between the initial state and the requested state. And these two examples of invariants over here, the number of trees and the number of squirrels, are the perfect examples of invariants that are not capable of detecting or discriminating against two different states, the initial state and the final state. We have 666 trees at the beginning of an experiment, and we have 666 trees at the end of an experiment. Whether this experiment, for example, if that experiment succeeds, and so are the squirrels. 666 squirrels at the beginning of an experiment and 666 squirrels at the end of the experiment, if at all it is possible to put all 666 squirrels onto one and the same tree. As such, we now understand that the structure of the invariant or of an invariant that may be helpful in this problem has to be slightly more complex or slightly more involved, because as instruments, the invariant for the number of trees and the invariant for the number of squirrels, these instruments are too blunt. They do not really help us immediately, even though, yes, fundamentally, yes, these two invariants sit at the foundation of any solution, because we know this is precisely what helps us build a solution on top of this foundation. The number of trees remains the same, the number of squirrels remains the same also throughout the entire problem. We do build our solution on top of these two invariants, but immediately, in a technical sense, these invariants are not really helpful. We feel that the structure of an invariant that may be helpful has to be sensitive to both at the same time, both the number of trees and the number of squirrels. And this is where the notion of beauty in mathematics comes in. In season 1, episode 1, I argued that mathematics is an art form in just the same way as painting, drawing, sculpting, musical arts, or literary arts. And the idea of the beauty of a piece of artwork as a whole applies to this, let's say, visual or musical or literary arts in exactly the same way as it is applied in mathematics. A painting that you saw just a few seconds ago is just my personal preference. This is one of my favorite paintings of one of my favorite artists. But again, my taste should not affect your taste. And the idea that I'm trying to deliver is that just because you're studying mathematics, theoretical physics, and computer science does not mean that you should completely walk away and forget about all the other art forms. Quite the opposite is true. It is a good idea to learn or try to learn, for example, how to play a musical instrument, or try to learn how to paint, sculpt, draw, how to write a piece of music, or how to write a short story, for example. Because that attempt to learn how to do this or that form of art will only enrich you as a mathematician and will add one extra level of depth and one more dimension to your mathematical maturity. The idea here is the following. It is a good idea to try to discern or try to see beauty from ugliness in the mathematical constructs that are put by others first, and then be brave enough and honest enough with yourself to qualify the constructs that you put together as beautiful or ugly. And admittedly, yes, initially it is most likely that the constructs that you put together will be mostly kind of sort of ugly and mostly kind of sort of awkward. And that is perfectly fine. We all have to start somewhere and learn somewhere. But the idea here is do not stop at that point, because if you were able to come up with a construct that is admittedly awkward and ugly, okay, this is fine. If that construct is useful, solves a problem, given problem correctly, then game over. This is a solution of a problem, but trying to polish that awkwardness and ugliness away into something that is more beautiful, that will precisely, like I said before, will add one extra level or one extra dimension and one extra level of depth to your overall mathematical maturity. And speaking of beauty in mathematics as a wholesome, here is an example. And that example, again, for those who are more or less familiar with how, for example, visual arts work, you will see that in a work of visual art, when such a work is beautiful, then every detail in that work is in a proper position and the proper size, relates to the whole in a good way. Nothing is sticking out, nothing is sinking in. And in mathematics, it works exactly the same way. When a mathematical construct is beautiful, then every detail that follows that construct is in the right place and in the right size. When John von Neumann and company in the early 1940s were developing the first electronic computer in Princeton, New Jersey, USA, Johnny von Neumann suggested the following computational model. Command, CMD, at an address. Command at an address. In the earliest segments in this episode, you saw me using a very similar notation for capturing the process of squirrels jumping from one tree to another. Recall that I used X squirrels at a tree number 7 or number 8 and so on. And I used that notation precisely because my brain is burdened with this bit of historical trivia, historical knowledge. But In this case, we get to witness the fact that when we capture a mathematical idea with a successful or a proper, in some sense, notation, that notation already can be both suggestive and helpful. How does that notation suggestive and how does it help us? Well, here what this notation suggests is the product of the number of squirrels times the tree number. And the ordinal position of the tree on a circle is what? Is precisely an address of that tree on the circle amongst the many. That's on the one hand. On the other hand, if you have a little bit of a physicist in you, you may recall that when the center of mass of a discrete system of a finite number of material points is calculated, then we use the following construct. The sum of masses mk times the distance of the points from a certain arbitrarily chosen point, the sum of the products. And again, this is probably or maybe a relatively tall order, but if you have seen enough of mathematics, then the construct of the sum of products of two elements is actually quite popular in the, let's say, power series expansion of a function. If a function can be decomposed into its power series, we use what? We use the same notation when we construct the sum of some coefficient times certain power of the argument, let's say x, where n varies from 0 or 1 depending on the situation. In the Fourier series decomposition of a function is, what do we use again? Sum of products, the Fourier coefficients, and the value of the trigonometric function of cosine and or sine. In complex analysis, the Lorentz series decomposition of a function is again what? A sum of products, the coefficient and the construct known as, for example, z minus a to the power of n, where a is the pole of the function. Yet in another case, according to the Cauchy's residue theorem, in certain cases the value of the contour integral is equal to what? Product, sum of products, the residue of the integrand evaluated at a pole times what? Times the winding number of the curve around that pole. So lo and behold, depending on your level of mathematical knowledge, your path and your mileage will definitely vary, but in this case it turns out that a beautiful construct that is useful to study in this case is the following one. In general, this construct will be a function of time, so we'll designate it with s of t, and that will be precisely the sum of products, the ordinal number of the tree, where k varies from 1 to n, times the number of squirrels that sit on the tree number k at the moment of time t. So this will be s of k, and this in general, this will be a function of time. So now that we have this construct over here, we'll refer to it as uppercase S. You may use any other letter that you guys like. But now, why does this construct is helpful and why is it beautiful? Well, the reason why this construct is helpful and beautiful is because everything falls in the right place when we analyze or when we drag or troll this construct through the jumping sequences of our squirrels. In order to make sure that everyone understands what will unfold, I will analyze this first case slowly and thoroughly, and I will analyze the consequent cases a little bit faster. As such, we carefully write down the result of the jump, let's say clockwise jump from the tree number k to the tree number k plus 1 in the case when the tree number k is strictly less than n. In other words, the hop over, if we number our trees somehow, let's say 1, 2, 3, and so on, here there will be the tree number n. This transition from n to 1 and from 1 to n we will consider in a separate analysis, in a separate case. As such, assuming that the tree number k from which the squirrel jumped to the tree number k plus 1, again here we assume that I number the trees in the traditional clockwise notation, 1, 2, 3, 4, 5, and so on. It doesn't really have to be. This is just to make the analysis easier. In this case, we write down the original value of the sum before the jump. So before the jump, what do we have? We have the tree number k times the number of squirrels on that tree at the moment of time t, let's say t, plus the tree number k plus 1 times the number of squirrels k plus 1 on it. Now, after the jump was executed from the tree number k to the tree number k plus 1, we'll refer to it as a clockwise jump. So at time t plus 1, what will we have? What is the transition from one structure to another? Well, in this case, the number k will be one and the same. The tree number remains the same times, but the number, remember our early analysis, the number of squirrels on the tree is now diminished by 1. Plus, again, the tree number k plus 1 remains the same, but what changes? Well, the number of squirrels on the tree number k plus 1 increased by 1. You see? This is what happens in the unit of time 1 unit of time, let's say 1 second, when a squirrel jumps from the tree number k onto the tree number k plus 1, when the number, the ordinal position or the ordinal number of the tree is strictly less than n and greater than or equal to 1. What do we do now? Well, this is where all my ideas about beauty, art, and things like that fall into place and manifest themselves. Look at what happens now. What happens now is nothing more than not even middle school, this is kindergarten arithmetic. We multiply, we open up the parentheses where we need to. What do we have? Look at this. K times sk minus k plus k plus 1 times s, k plus 1 plus k plus 1 times 1, open up right away, k plus 1. Do you see what's going on? This transformation should cause no trouble. Everyone should understand what transpired over here. We simply opened up the parentheses, but what do we see now? Negative k, positive k. Cancel, cancel, and what do we have now? Let me use the blue chalk to highlight this term and this term. This is what we had in our sum at the moment of time t. And what do we have now? We have the same thing here. You see this guy? We're saying the same guy. Let's thread the needle over here. We have him here. And what do we have? We have just plus 1. So that means that when one squirrel jumped, let's say clockwise from the tree number k to the tree number k plus 1, when k is strictly less than n, then the value of the sum t changed by positive 1. So depending on your taste and desire to do manipulations or record this symbolically, we will say that in this case, the delta is equal to plus 1. So what does the delta mean? Well, technically we can write through this string of manipulations, we can say what this is s at the time t plus 1, and this was what? This was, let's say, s at t plus 1. You see, so if from the value of our construct s of t at time t plus 1, we subtract the value of our construct at time t, the previous bit, if you will, we will get what? We will get the positive 1 plus 1. This is what the plus 1 means. So here we can even write down the following. In order to capture the fact that this was a clockwise jump and clockwise motion is usually taken to be negative, we can say that the value of our construct with a minus sign over here, where minus basically designates the negative direction, which is counterclockwise, then this is what happens, s minus and s minus, if you will. This is just capturing one situation, one case when the squirrel jumped from the tree number k onto the tree number k plus 1. And now we'll consider what will happen to our quantity s of t when the balancing jump is executed from the tree with a larger number towards the tree with the smaller number. Very well, now let us consider what will happen if the balancing jump, let's refer to this jump as counterclockwise. Again, my notations here are mostly logical. You can pick different ones. And those of our viewers who are comfortable working with the same variable k, go ahead and do that. If you're picky or a fussy kind, then okay, fine, we'll work with a different one. So here the jump unfolds from the tree number j plus 1 towards onto the tree number j. Again, we have a strict inequality j is less than 1. We'll consider the transition from n to 1, from 1 to n in a separate analysis. But what will happen over here? Well, we can already write down, we know what is going on. We can write down the expression that will be the value of our construct s, uppercase s. This is lowercase s. And if you guys don't like the competition or the collision of lowercase s and uppercase s, use sigma or something else. So here when the squirrel jumps from the tree number j plus 1 onto the tree number j, what will be the structure of our relevant terms? Well, the tree number j will remain one and the same, but the number of squirrels on the tree will be increased by 1. And then in our construct, the tree number j plus 1 will also remain one and the same, but the number of squirrels, let's say j, the number of squirrels on that tree will decrease by 1. You see, the number of squirrels on the tree number j, s sub j, will increase by 1, s sub j plus 1, and the number of squirrels on the higher number tree, j plus 1, will decrease by 1. Again, straightforward kindergarten variety arithmetic. J times Sj plus J times S sub j plus J, plus, we'll grab this whole thing over here, J plus 1 times Sj plus 1, J plus 1 times S sub j plus 1 minus 1. So we multiply this usual suspect by negative 1. So minus j minus 1. And what does this string of manipulations tell us? It tells us that this positive j and negative j cancel each other out. And from this it follows what? What can we write? Well, we can write that in this case, as, let's say, because counterclockwise direction is usually taken to be positive, so the positive component of the construct uppercase s of t plus 1 will be what? Whatever we had at the moment of t, and then minus 1. So in this case, if we subtract this term from this term, our delta will be, in this case, will be what? Negative 1. You see? -1. And in this case, we have more cases to analyze, more ways to combine the jumps. But if these two jumps, this is how the one jumping sequence unfolds, then what does it mean? In the first case, the value of the sum increases by 1. In the second case, the value of the sum decreases by 1. And the net change, when both squirrels jump according to the rules described in the problem statement, then what will happen? The value of our s, sum s, will not change at all. So these two guys, the net change, I don't know, let's write large delta, will be precisely big fat 0. And now let us analyze what will happen if the jumps unfold precisely from the tree number n onto the tree number 1 and from the tree number 1 onto the tree number n. Excellent. Let us now consider the next sequence, the clockwise jump from the tree in our notation from the tree number n onto the tree number 1. In this case, let us study the structure of our sum of products Sn. What will happen? The tree number 1 will gain 1 squirrel, while the tree number n will lose 1 squirrel, Sn minus 1. And how does this sequence of changes unfold? Well, we have 1 times S1 plus 1 plus n times Sn minus n. You see again, nothing complicated over here. Kindergarten arithmetic, 1 times this sum over here becomes these two terms, and n times this difference becomes this. So here again, if you want, let me use blue for example. Here you recognize the original, and here you recognize the original term. And what does that mean? What will we write for the delta over here? Delta in this case will be what? So we will write it like this. The sum in the negative direction at the time t plus 1, this is intermediate value of our sum when the squirrel jumped from the tree number n to the tree number 1, will be represented which way? The value of whatever s was there at a time t minus n minus 1. Would you agree? Plus 1 minus n minus n minus 1. So here the delta is negative n minus 1. That should cause no trouble. And then for the balancing act, we will consider the case when in the counterclockwise fashion from the tree number 1, the jump is executed onto the tree number n. Lastly, let us consider the case when the balancing counterclockwise jump is executed by a squirrel that was sitting on the tree number 1 onto the tree number n. What will happen in this case? Well, in this case, the tree number 1 will remain 1 and the same, but the number of squirrels on the tree will, as one, decrease by 1, and all the remaining terms will be the same. The tree number n will still remain the tree number n as it was before the jump and after the jump, but it will gain 1 squirrel Sn plus 1. So what does that mean? Let us try to do that right away in our mind's eye without any pen and paper. Here in this summand, we will recognize our original term. Here, this usual suspect will be our original term. What will be here? 1 times negative 1 will be minus 1, n times 1, 1. So what will be the net change? In this case, we can write it down right away. In this case, the net change will be positive and minus 1, so that we can write that the positive component associated with the positive direction at time t plus 1, the intermediate value of our construct s associated with the counterclockwise jump in the positive direction will be s of t, whatever it was at the moment of t, plus n minus 1. So that's the delta. That's the positive change in this case. And now that we have all the possibilities clearly evaluated, we can now look at possible combinations of how squirrels can execute their jumps. Now that we have all the possible legal transitions of squirrels over the trees on the books, let us analyze the possible, not permutations in this case, but combinations of things. We already did one over here. If it so happened that two squirrels changed their positions in a way that's covered over here, the net change of our quantity S is 0. The magnitude of our quantity S over here does not change. When and if two squirrels decided to jump from the tree number n onto the tree number 1 in a clockwise fashion, and in the balancing act from the tree number 1 to the tree number n, again, here we do not really have to do any arithmetic at all. We already know that the trees are distinct mathematical objects. We treat our squirrels as indistinguishable. Two squirrels over here basically executed what, from the theory of permutations or the theory of groups, a transposition. Nothing changed, but our computations over here keep us honest and verify. Yes, it's true, the intermediate change in the first case will be negative n minus 1. The intermediate change from the second jump will be positive n minus 1. Plus and minus cancel each other out. If that is the jumping scenario, then again, the big delta over here will be 0 again. And what are the remaining possibilities over here? Well, we can have, for example, a squirrel jump. Let me use the red chalk over here. Clockwise, I'll put the crossbar on top. This is not conjugation from complex analysis. This is just in some syntactic sugar to figure out what's going on. Clockwise jump from from the tree number k to the tree number k plus 1 under this constraint, the k is strictly less than n. But for the balancing act, what do we have here? We have this guy right here, this guy. So in this case, what are the possibilities? Let's write down it carefully. The delta in this case, I'll use the red chalk, plus 1 plus n minus 1. So the delta in this case will be plus 1 plus n minus 1 will be what? Will be plus n. So far so good, excellent. And let us do this. I'll use the blue chalk for the other case. What's the other case? Counterclockwise jump from the higher number tree to the lower number tree under the constraint that logically the boundary is not crossed, can be balanced with the clockwise jump from n to 1 over here. So these two cases can be combined also. Let's put it this way. So what will happen in this case? The delta in this case, in the blue case, we have negative 1 minus n minus 1. What will happen? Negative 1, negative 1, negative 1, positive 1, minus 1, plus 1 cancel each other out. What's left over? Minus n. So in this case, let's write down the delta will be negative n. And if I can steal some room and make a big mess out of this, somehow this And let's combine it with which one? With this here. Let's write it down over here. The delta will be positive n. And what does this straightforward, beautiful kindergarten variety level analysis tell us? It tells us that under any legal jumping sequence, one jumping sequence, our quantity S of t either does not change at all, or changes precisely by plus or minus n, where n is the number of squirrels and number of trees. So now, whenever we see the following construct: integer, whole number, a product of any two whole numbers is another whole number. So what do we have? We have an integral quantity plus minus n. And what does such a construct suggest for an invariant? Well, whenever we see an integral expression, something, full bar plus minus n, an evident choice for a successful invariant is that whole construct modulo n. In other words, if we write down, let's say this way, S of t, if we write down plus minus n, this is our net change modulo n is our candidate for the invariant. Why is that? Well, because the operation of computation of residue upon the integer division by n is blind to the act of adding the modulus to our integral quantity or subtracting the modulus from our integral quantity. As such, we can really erase this and leave it like that, and this is our successful. We can even, let's do it this way, make it neater. We can subtract, remove the parentheses and say that S of t mod n modulo n is our candidate, and this is precisely the situation that I was driving at, guys, in order to demonstrate to everyone what does it mean that not all invariants are created equal, in the sense that a successful invariant is an invariant that is capable of detecting or discriminating between the values associated with the initial configuration and requested configuration. In the initial state, we have precisely one squirrel sitting on each and every one of 666 trees in the one flying squirrel per tree fashion. Remember the original problem statement. And what does it mean? What kind of news is that for our quantity called S of t? Well, this is actually good news, because then at the moment of time S of 0, our sum looks as follows. The sum of k from 1 to 666 of k times precisely 1. And what is that? Factor 1 out. We already know how to compute that finite sum of integers, and the answer here is our favorite 666 times 666 plus 1 over 2. And what does that mean? Well, that means that this sum can be represented as 333 times 666, right? 2 and 666 cancel out. We have 333 over here times this sum over here plus 333. And what does it mean for our invariant? Well, in this case, the invariant at time, let's say 0, is equal to that horrible expression over here, modulo 666. And what is the answer? Well, the integer division of this expression upon 666 will produce or yield the residue of 333. Exactly. 333. Now, let's say at a hypothetical moment of time t, so let's write it down over here with it cross like this, the s of t less than positive infinity, that's basically a fancy way of saying in the finite amount of time, all the squirrels somehow magically manage to gather on one and the same tree. What does it mean? Well, it means that s of k for all k's is 0 except for one specific one. We do not know which one. Well, that means that the number of squirrels on the tree will be what? 666 times certain number, let's say k, where k evidently varies between 1 and n. And what does it mean? The magnitude of this here sum modulo 666 is what? 0, exactly. So the invariant at time t, some finite amount of time, will be big fat 0. And what can we say? 0 is not 333. 333 is not 0. So the answer, so in general, what does it mean? It means that we solve the problem, and the answer to this specific problem, when we are given 666 squirrels and trees, the answer is in the negative. In no finite amount of time, the 666 given squirrels can gather or bunch up on one and the same tree. And now that we answered this specific question, we can think a little bit more generically. In the previous segment, we managed to find an invariant that was capable of detecting or discriminating between the initial state and the final state, or the initial configuration of given objects and the requested or the final configuration of the given mathematical objects. And because that invariant produced two distinct values, 333 in one case and 0 in the other, evidently 0 is not 333, 333 is not 0, we answered the question posed in this specific version of the problem in the negative. No, in no finite amount of time, the given 666 squirrels can bunch up on one and the same tree. But now we want to reason slightly more generically and try to figure out what is really going on with this problem. We already saw that after one legal sequence under any possible combination of jumps, the value of our quantity called S of t can either not change at all or gain or lose precisely n, the number of usual suspects in this problem. That means that after some finite number of jumping sequences took place, then what will be the value of S of t at that time? Well, it will be S of 0 plus n, remember plus minus n, times m for a suitable integer m, which could be evidently a negative whole number, a positive whole number, or 0. That is on the one hand. On the other hand, let's say all the squirrels somehow did manage to gather on one and the same tree. And what does that mean? Well, we already saw in the previous segment that then the value of that sum will be n times, for example, let's use q. We know that in this case the values of S of k will be 0 for all the trees except for one specific tree on which all the squirrels managed to hop using the legal jumps, a sequence of legal jumps. We call this tree K. All n squirrels are on that tree. So now let's loiter around this expression over here. We know the magnitude of, we know the value of the sum as of 0. We already did it in the previous segment with specific numbers, but in general it will be n times n plus 1 over 2. We already know that much because precisely the s of k at t0 is precisely 1, so we have a sum of the initial consecutive positive whole numbers 1, 2, 3, 4, 5, and so on, plus n times m equals n times q. In this case, evidently, if n is equal to 0, we have no problem to speak of. So thus, we can safely assume that n is not 0. Let me record it somewhere here. N is not 0. Consequently, it is safe to cancel one copy of n from everywhere. Then multiply this result by 2. What will happen? These 2 and these 2 will cancel out. We'll slug in 2 over here. We'll slug in 2 over here. And what is the result? Well, the result will be as follows. N will be equal to 2 times q minus m minus 1. You see, this is the real deal with this problem so far. This is the real deal. In other words, if our squirrels did manage to bunch up on one and the same tree under the specified jumping rules, then that number and their number must necessarily be what? Must be odd. This number must be odd. So in terms of our favorite if P then Q implication, if P then Q, if P then Q, what did we manage to find? The premise of this implication P is what? That the squirrels did manage to gather on one and the same tree. And then what's the conclusion? Then the number of these squirrels, that's the conclusion, must be odd. We know that, let's say, a direct statement like this, if P then Q, and its contrapositive are logically equivalent. Logically equivalent. And how do we construct a contrapositive? Well, we take the premise and the conclusion, we rotate them around the then clause, and then we negate them. So we will construct if not Q, then not P. And what does it mean? If the number of squirrels is not odd, then they will not be able to bunch up on one and the same tree in a finite amount of time. And if the number is not odd, then it's even. Remember all the highbrow intersection of distinct equivalence classes modulo n. If a number is not odd, then it is even. And thus, what did we prove? That if the number of squirrels is even, which was the case in our original problem, 666 is an even number. If the number of squirrels is even, then they will not be able to gather on one and the same tree in any finite amount of time. And also remember that early on, when we experimented with smaller numbers, we realized, or we discovered, pick your favorite verb that describes this process. We figured out how to put all the odd number of squirrels onto one and the same tree in a finite amount of time. Remember, we had what was the deal? If n is representable as 2m plus 1, then the number of units of time that was needed was m times m plus 1 over 2. So in that case, what did we also prove? Well, we proved the direct statement, if P then Q, and we proved its converse. So in other words, we proved if the squirrels did manage to gather on one and the same tree, then their number must necessarily be odd. And conversely, we already showed, we produced one valid and correct algorithm, which tells us what? If the number of squirrels is odd, then following this algorithm, this is how it is possible to put all the squirrels onto one and the same tree. So we proved a direct statement and its converse. So in mathematics, this is usually compressed into if. So at the end of the day, what did we prove? We proved that the given squirrels can bunch up or gather on one and the same tree in a finite amount of time if and only if their number is odd. Again, look back to my claims that I made in season 1, episode 1. Mathematics is an art. Did we shuffle some numbers? Yes, we shuffled some numbers. We shuffled some formulas, but fundamentally, we had to produce or generate, showcase our ingenuity, creativity, and improvise a little bit and construct a quantity that came out to be quite useful. And what is the definition of a useful invariant? An invariant is useful if it is capable of detecting the difference between the original state or the original configuration and the final or the requested configuration. So I recommend that you guys play a little bit, maybe go back to our previous segment, and instead of 666, which I picked just for amusement purposes, see what happens if you slug in, for example, 667. What kind of answer will you get with our sum when 667 squirrels are distributed initially over 667 trees located in the circle, and so on. Now, this is it for the mathematical problem S2M50, and we will move on to a new challenge next. In the mathematical problem S2M51, on a tree, there lives a happy family of chameleons, each of which can be only one solid color, red or green or blue. Just to make sure that everyone is on the same page, no partial coloring or multiple coloring in this case is allowed. In other words, each and every chameleon in this happy family of chameleons can only be completely and only red, or completely and only green, or completely and only blue. Three colors, RGB, red, green, and blue. Now, whenever any two chameleons from that family of the same color meet, then no color exchange happens. In other words, if two red chameleons run into each other on the tree in their daily routine, then no color change happens. They both stay red. If two green chameleons meet on a tree in their daily routine, then they both stay green. And if two blue chameleons bump into each other, then they also stay blue. However, if any two chameleons of distinct colors meet, then they both simultaneously and, let's say, instantly or very, very quickly change to the remaining color. And I depicted this rule in the table on your right. In other words, if one red and one green chameleons bump into each other, then they both become blue. If one red and one blue chameleons meet, then they both become green. That's the remaining color over here. That's the remaining color over here. And if one green and one blue chameleon meet, then they both become the remaining red color. And let's say during their daily routine over the lifetime of, let's say, one day, again, every second, every your favorite unit of time, this color exchange takes place. And the question is the following: can all the chameleons in that family under these rules of changing colors turn one in the same color in a finite amount of time if initially we're given 27 red chameleons, 25 green chameleons, and 23 blue chameleons? Now, as a fair warning, as a heads up, this will be our final problem that deals with the study of the invariant problem solving approach. Starting with the following problem, we'll look at something else. So this is it for this episode. Thank you very much for watching. Thank you for your time. I will see you in the next episode, in which I will show two solutions of the problem S2 M51.